Okay, so all right, I believe recording started. So welcome back. We are now on to miniature number 27. And like I said yesterday, this is probably a narrative in a similar spirit to what we saw last time. The idea is to see if we can leverage SWOT-ZIPL to get a fast randomized algorithm for a problem relative to the brute force, the natural brute force approach. So what's our problem for today? We want to test if a binary operation is associative. And I guess we are familiar with associativity from, I don't know, kindergarten or something. Not me, but maybe most other people. So a binary operation, of course, is an operation that acts on two things in a set and produces a thing from the set. So binary operation on a set X can be thought of as a function that maps x times x to x. So you pick a pair of ordered elements and return an element from the set X. And it's said to be associative if the okay, I was going to say the order of operations don't matter, but I guess that's not the right thing to say. Okay, so let me just say it like it is. So if you want to do the operation on X, Y, and Z, it doesn't matter if you do it on X and Y first and then Z, or whether you do it on Y and Z first and then on with X and the outcome of Y and Z, right? So that's associativity. I think it's hard to come up with natural examples of binary operations that violate associativity. I don't know if anybody has any trivia on this. I think there is something mentioned in the miniature, but I could not make any sense of it. I can try to pull up the example, but most of the natural operations tend to be associated. It's a hard, I think it's a hard property to violate. I mean, of course, you could probably artificially create binary operations that
No, there's a
violate.
very natural one actually.
Oh, there is a very
Uh,
natural.
yeah. Bread and butter. NAND gates.
Oh, NAND
Uh,
gates. Okay, all
yeah,
right.
so they are not associative.
Okay,
And that results in
a lot of problems.
eventually NAND gates getting used in characterizing some complexity classes instead of the usual Boolean gates. Yeah.
All right.
So,
Okay.
in fact, this was part of Valiant's thesis, in fact. Okay, so context-free grammars also have the similar property.
Um,
And okay, so this was part of Valiant's thesis a long time back. Yeah.
oh, very nice. So for the NAND gates, I think just so you're saying the NAND operation, the negation of AND as a operation applied to Booleans is not associative?
Yeah, it is not associative, and so is cross product. Everybody is familiar with vector cross product, A cross B. That is not associative either.
Oh, okay. All right. That's a good
Yeah.
reminder. I think that probably, yeah. In principle, I should also know, but yeah, it's not
No,
so.
you can just try I cross
Right,
J.
right.
Okay. I cross J will give you K.
Right.
And then I cross K will give you some minus J or something.
Okay,
Okay.
right. Fair
But if
enough.
you do the first I cross I, you get a 0 and therefore it will remain a 0. Yeah.
Okay, interesting.
So it turns out that these are important things. Yeah.
Okay, nice. That's yeah, the cross product and the NAND gates. Yeah, I think those are very nice examples. The one in the miniature is multiplication of the Cayley octonions, and I didn't even have the heart to look that up, but I mean, probably it's something that's quite nice. I should probably have looked it up, but I was, yeah, it's not something that I unfortunately had time for before this session, so maybe later. Okay, subtraction and a plus b by 2 is not associative. Okay, that's interesting. Thanks, Jagdish, for those examples. So a plus b by 2. Yeah, okay. I think you're probably right about that. I have to just pass that in a bit. But yeah, multiplication, I think I can see that that's not associative. And arguably that's it's a natural example. Over integers, I guess. Yeah, fair enough. Okay, so then there are apparently nice examples of things that are not associative. It just seemed like Yeah, for some reason I was blanking out when I was thinking about, okay, how do we get things to not be associative? But okay, so I think I'm now suitably filled in, so thanks very much. So now we want to test if a given binary operation is associative, and I guess we are restricting ourselves to finite sets because otherwise this can be a tricky question to model algorithmically. So imagine that X is a set with n elements, and the binary operation is given to you as a table. So you can simply read off the operation by just doing the row column thing. So the binary operation acting on whatever, two things would just be look at the row and the row indexed by the first thing, the column indexed by the second thing, and whatever you read off here is the outcome of the operation. So that's how the binary operation is specified. It's specified with n squared entries. So you could think of n squared as being the length of your input. And if you wanted to check if this operation is associative, you could potentially just test if the definition holds. So you could go over every triplet and test the definition. So that would be, let's see what that would amount to. So this is one table lookup, and then you get some answer. And that answer with Z would be another table lookup. Then this is one table lookup, and then that answer X combined with that answer would be another table lookup. So that is 4 table lookups per triplet, and then of course an equality test. So we are assuming all the table lookups and the equality tests are constant time. So this would be an algorithm that's n cubed times. So it's asymptotically worse than linear in the length of the input. So that's the brute force. That's the brute force algorithm, order n cubed. So let me know if you're good so far in terms of the setting up of the question and the baseline. The baseline is that we have an n cubed test for associativity, and we want to know if we can do better. And it turns out that we'll see a randomized algorithm which has a 1/2, a failure probability bounded by 1/2, one-sided failure once again, which actually runs an n squared time, which I'm thinking of as being linear in the length of the input. So give me a +1 if the notation and the setup looks good, and then we can go on to coming up with the nicer algorithm. Okay, in the miniature, as a warm-up, there is a little bit of a couple of lines of discussion about what would be a natural randomized algorithm for testing associativity. So if you have randomness, what would you perhaps do? The brute force algorithm checks every triplet. If you have randomization, what would be the natural relaxation of the brute force approach to leverage randomness? Instead of checking every triplet, what would you check? And let's say you're aiming for an n squared running time. So you can ping n squared things. And again, assume that table lookups and equality tests are free. Okay, so maybe I should just step back and confirm if the algorithmic task is clear. The input is this n by n table, right, which is indexed by X on both sides. And what the table gives you is information about what the operation does. The operation could be, I mean, I suppose you could have operations that have more succinct descriptions. For example, you could also have black box access to an operation where you have a black box. I think sometimes it's called oracle access. I suppose you could have a situation where you can feed this oracle your 2 inputs and it'll tell you what the binary operation returns. But instead here we actually have the operation given to us very, very explicitly. Okay, so that's the setting. And we simply want to know if this operation satisfies a certain property. In this case, what we want to check for is associativity. And yeah, I mean, I suppose you could ask other questions if you wanted to check if the operation is commutative, for instance, that A times B, I'm going to say times instead of saying whatever this absurd thing is. It's O dot in LaTeX. I don't know if there's a nice way of pronouncing this, but okay, I'm just going to say times. So commutativity would be A times B equals B times A. And this you can probably check by looking for symmetry in this table. Associativity is a little bit of additional headache because you have to check for this thing here, that x times y times z is x times y times z. So that's, sorry, I don't know if the pauses are indicative of the bracketing, but anyway, this is what we want to check for. And you could do that manually by doing, by going over all the triplets and checking if these values amount to being the same. And the first time that you have a violation, you can just stop, because then that's even one violation of the rule is enough to declare that the binary operation in question is not associative. So you could do that, but that would be examining in the worst case. If the operation turns out to be associative, then you're looking at n cubed triplets. Given a triplet, it's easy to do this check. Like we said, 4 table lookups and 1 equality test. So that's easy. But you still have to do n cubed of these checks, right? So that's the baseline. And is that clear? Is that okay? Like I said, we might be used to thinking about binary operations to find an infinite set. So this may require a little bit of a recalibration of the imagination, but X is a finite set. The operation is given as a table. The input is these n squared things. And we're simply checking for associativity. All right, thank you. Now, one question is, if we had the power of randomization at our disposal, then instead of checking each triple, what would be a natural thing to do? Like, can we somehow check most triples and get away with it? And if we have to check, I mean, we're doing randomization, so what would be one way of putting it? Like, what we are looking for is violations of associativity. And instead of trying to test for all possible violations, can we hope that maybe, given that we've been looking at randomized approaches the last couple of times, basically we are now letting go of the ambition of getting it right all the time, but can we get it right most of the time, or a reasonable amount of the time? That's the question. So if we let go of perfectionism, then one thing, okay, so I don't know, I thought I had a description. No, I didn't put this on the slides. Okay, so one thing that you could do is, I was quite sure that I did. Let's see. Okay, so this is our goal that we want to, okay, so it's on, okay. It's one slide further down than I anticipated, but okay. So our goal is to come up with the n-squared algorithm, which is randomized, and it has one-sided error, meaning that it never says that an associative operation is not associative, but if the input is an operation that has a violation, then it may miss out on pointing this out. But that happens with probability at most half. Therefore, if the algorithm reports no, you can be absolutely sure that the algorithm is correct. But if the algorithm reports yes, it could either be coming from here, or it could be coming from here. It could be a false positive. Okay, but that's going to happen not too often, is the hope. Okay, so that's the goal. And the question was, well, imagine that, you can do, you can do whatever in order n squared time. What would be a natural randomized approach? So, okay, so Abhinav's suggesting that we fix Z, maybe fix your favorite element in X, and pick X and Y at random. So there are n squared choices for, in fact, if you fix a Z, you actually could brute force over all choices of x and y. That would actually be only n squared time. So I would maybe flip your description around to say randomly pick z and then go over all possible x and y. That could be a reformulation. But yeah, basically, I suppose, yeah, that's kind of the idea. That's exactly the idea, that we do a random number of tests for associativity. Instead of going over all possible triplets, we go over some n squared of them. So let's say we're just sampling from the space of all triplets, and we sample n squared times and test for associativity. So that's exactly what I was after. So thanks, Abhinav. Now, what we want to do is try and reason about the success probability of this algorithm. It seems like a really natural thing to do. But unfortunately, we are in this situation where an operation is not associative, even if it fails the associativity definition on a single triplet. And unfortunately, it's possible to design binary operations which have exactly one violation of associativity. So you have the C of n cubed triplets, of which only one, or let's say only a constant number of them, are in violation of our definition, and everything else is okay. So if you pinged only n squared of them, right, then you would still have the wrong answer with a rather low probability, so not constant. So the problem is that, yeah, if there's only one in n cubed triplets, which is a problem, then by pinging n squared of them, your success probability is going to be only 1 over n, right? So does that make sense? Give me a +1 if you see that the natural randomization idea can fail quite dramatically. It's much worse than what we want. Yeah. Okay. All right. Thanks. So this would be a natural thing to do, but it's not good enough. So we are going to try and do more. And once again, the hope is to somehow bring in polynomials in a way that our failures can be mapped to a situation where we are hitting zeros of a low degree non-zero polynomial. So if we can make that association, then just like last time, we will somehow be in business. And to be honest, I didn't spend any substantial time trying to think through this on my own. So I cannot say if the ideas here can be reasonably natural or not, but at the moment, I really don't have a way of motivating how to think about bringing polynomials into this picture. So we're just going to go over the mechanics of what's going on. And yeah, Jagdish, this is a great question. I actually don't know. I only very briefly thought about this claim, which is left as an exercise in the miniature. And I think what you could do is start with a set which is associative. So you can take your favorite operation which is associative, pick any. And I was assuming that maybe if you do a very small perturbation somewhere, then, but the tricky bit is how do you perturb something while not disturbing too many triplets? So it's not completely sure, but my guess was that you would want an operation that looks almost completely associative. So its edit distance from an associative table would probably have to be low. And I thought you could engineer that. It seemed like, at least if you, I don't know, if you want to say a constant number of violations, I feel like that should be doable. But yeah, if anybody has any ideas on how to actually come up with a concrete construction of binary operations that have, let's say, only a constant number of violations, because even that would lead us to trouble, that would be nice. So yeah. Okay, so I mean, I think it's a good question to think about, and I'm going to see if we circle back to it. If anybody has any ideas, then let me know in the chat, or feel free to just unmute yourselves as well. But for now, just maybe in the interest of time, let's try to move on to the randomized algorithm that does have a nice success probability. And like I said, this is something that we should definitely come back to now or offline. Okay. All right. So here's what we're going to be working with. We're going to fix a finite field, and I didn't. Okay. So K is going to be, we didn't have space in the slides earlier, but let's just take K to be some field width. So I think in particular, they choose this to be a field with 7 elements for some reason. And I'm assuming this is what this is. This is hopefully F7, and that should work. They do say that we can make this work over R or a larger field. Again, this is something that I haven't checked, but we are going to fix K to be a field with 7 elements for now, because as we will see, the calculations go through just fine. I don't know why it has to. I mean, I don't know if 7 is particularly auspicious, so we will check this as we go. But for now, let's just run with this. So K is a finite field with K elements. So vectors are the vector space that we are considering is a vector space with n coordinates. So the coordinates are indexed by our given set X, right? And the entries are from K. So this is the vector space of interest. And what we want to do is, in some sense, we want to lift this again, this circular operation, which is defined on X, we want to lift it to the vector space here. So we want to define a binary operation on this vector space. And maybe this to some of you is possibly like a very natural thing. And yes, size of X is n. Thank you. Maybe I should put that down as well. I don't know why. So, and yes, size of X. And so yeah, X is n elements. And here is how we are going to try and adapt the circle operation to a binary operation on this vector space. So for that, first we are going to define some kind of a basis. So let E of X simply be the vector, which is 1 at the X index and 0 everywhere else. So that has, that's essentially, you can think of it as some sort of a basis. So for the example, for the table that we saw in the beginning, X was, the 4 suits. So imagine that they're ordered in this fashion. So E of X basically gives you, so remember that n was 4. We had 4 elements in X. And so we get, E gives us the mapping to what you might think of as a standard basis in the natural way. So give me a +1 if the definition of E is clear. E takes an element of X as input and returns the vector from K to the X, which has a 1 in the coordinate indexed by the input to E and 0 everywhere else. So here my indexing is kind of implicit. This is the heart, diamond, spade, and club. So that's what's going on here. Okay, all right, thanks. And now we want to define our binary operation on the vector space. So suppose we're given 2 vectors in the vector space, we write them out in the standard basis. We write them down in terms of the standard basis. And now to define, so hopefully this is like the usual way that you would write out any. So for example, if, I don't know, if U was, say, so elements are coming from K, there are 4 coordinates, because in our running example, which is the table that we saw right in the beginning, there were 4 elements in X. So let's say U is something like 4, 3, 0, 1 or something like this. So you would write this as 4 times E of whatever, this was the heart, and 3 times E of, what was it, diamond, and so on, right? So that's just the standard expression of these vectors in terms of the standard basis. And now to define the binary operation on U and V, we basically multiply out the sums. And when you multiply them out, notice that you're going to get, you're going to pick one thing from here and one thing from here, one summand from the first sum and one from the second. So you're going to get a sum with n squared terms, one for each pair of elements from X. And that term is going to be, well, you're going to multiply out the constants and then you're going to multiply E of X and E of Y. So now these are two standard basis vectors. And of course, we're trying to define this guy, so we don't really know what this is yet. But between X and Y are elements of capital X, and we have the circle binary operation between them. So is there a way that you would imagine using the circle operation to define the square operation here, given that now the square operation is just between the standard basis vectors? Any suggestions? It does feel like E circle Y should come into this picture somewhere. It seems very tempting to use the um, the given binary operation on X to define the square operation on the basis vectors associated with the elements of X. So let me know if you have any thoughts. I'll just pause for a few seconds here. Okay, maybe let me say this. We want E of X and E of Y to multiply out with the square operation. The square operation is a binary operation in k to the x. So we want this output to be an element of k to the x, right? But at the same time, I want to use, let's say z is x times y, where this times is the circle operation. That's the operation given to us on x. So what's one way that we have seen of associating elements of x with elements of k to the x? We've seen one map that takes elements of x to elements of k to the x. And that map is already being used here. So, I mean, we've seen only one anyway. So can we use that map to go from z, which is the given binary operation applied on x and y? Can we use that to go from the x space to the k to the x space? Today, I might have an example on the slides as well, which I'm not making use of. So, okay. Yeah, maybe I want to show you this. So suppose, for instance, X was hearts and Y was spades, and we're trying to define this. And we know that hearts and spades multiply to give us hearts again. So this is what we have. But now this is not, I cannot say that the square product on these two vectors is equal to a heart. I can't say that because I want something in k to the x. So how do I map the heart to something in k to the x? That mapping is actually already on the slide. So I'm just looking for a map that can transport me from x to k to the x. And I think a few slides ago, we did define such a map. So notice that E was something that transported us from elements of x to elements of k to the x, right? So, so in some sense, yeah, I'm just trying to come up with a definition here, so there are no wrong answers. But I'm just wondering if something here feels natural. So I want to define the box product of these two vectors, but these two vectors are not arbitrary vectors in k to the x. They're these basis vectors, which means that these vectors very naturally associate with some element of the base set x, right? But on the base set, I have this binary operation, right? So I can combine the things sitting inside the E. I can combine the things sitting inside the E using this table, right? So I have a natural looking answer here, but this answer is not type checking. It's semantically in the wrong space. It's in X. So can I use some means of transport to go from X to K to the X, and that'll give me my definition. So any suggestions on that? Or I don't know if I suspect that is something not clear about some of this notation, then let me know. We can go over it again.
As an aside, I think this is, I think, a very good example of a monad. So,
okay, I see.
People interested in programming.
Hmm.
So the idea is that you have an element, you have boxed it in something.
Mhm.
You open the box, then do whatever operation you want to, and then put it back in a box.
Right.
Yeah. So I think I'm assuming that's what you want to do here.
That's what I want to do here. Yes, and but I don't know anything about monads, so I'm going to take that as a given, unless you wanted to give some more context.
No, nothing. I mean, this is typically what happens in a monad. Monad,
Okay.
a lot of tutorials on the internet will say that monad is something that takes something of a specific type and then wraps it around another type.
Right. Okay. Interesting.
But now you can, you want to be able to do operations on the new type on the container.
Yeah.
Without writing your programs again.
Mm-hmm.
And the way to do that is, this is the definition of that.
Correct.
Open it, do the operation, and then close it. The language will do it for you. You don't have to bother about it.
Yeah. Oh, that's nice. Okay. Yeah, maybe now I can go and look up monads a little bit. I've been topic I've been avoiding forever, but okay, maybe. Yeah, okay, thanks. I think that's nice, and yeah, that's kind of exactly what I was hoping to get at. But okay, Jagdish, you were saying something?
Yeah, can you go to the previous slide?
Sure. If my keyboard cooperates, just give me a second. You mean the slide with the definition of E?
No. So yeah, I'm just trying to understand why this is a vector space.
Oh, I see. Okay. I don't think I spent any time on that. But isn't this your typical, how is it different from the normal, like you have n coordinates with entries coming from a field, and they combine as you would expect, right? Using the field operations.
In field operations, your inner product is commutative. This is not commutative. E of x square E of y is not equal to E of y E of x, right?
Wait, so are you talking about the space of these mappings?
No, as in
just k to the x.
How do you prove that this is a vector space the way you have defined?
So K is a field, right? So X is just a set, which I'm using just for labeling the indices, right? It's I guess it is really just an artificial thing. Think of it as just I mean, you could potentially think of this as Rn basically, but instead of R, I'm just using elements from a finite field. That's all.
No, that's the difference. You can't replace K by a finite field, right? Because if you replace K by a finite field, then your dot products and all become commutative. But here your set could be non-commutative.
Which set? X or K? So there are two things.
K. You can't replace K by F, right?
I'm replacing it with F7, yeah.
You can't do that. That's what I'm saying.
Okay.
Right. I think that's the reason why it's K and not just F7.
Well, so I think the claim in the miniature is that pick your favorite field with 7 elements and
Then how? Okay, let's go to the next.
Where do you get dot products like this?
No, just go to the next this thing. Next. Next slide. Next slide. So here I thought you were going to define a dot product between two vectors in your vector space.
No.
But this
No,
is
that's not what's happening.
This is just something else, right?
Yeah, some arbitrary operation. Yeah.
Okay.
Yeah.
I think, okay. So it is a vector space, but this is not a dot product. This is something. This is just
it's giving you a vector. I mean, the whole idea is that you want a vector, not a scalar. So that monad operation actually takes EFX, EFY and gives you a vector back. Yeah.
Yeah, exactly. Okay, maybe I should have been clear about that. What we are trying to define here is I mean, it's a binary operation on our.
I thought, okay, no, I didn't expect it was an inner product. I thought it was like coordinate-wise multiplication, but it is not that.
Right, no, we were trying to think the question, and the place where I paused was just to just to invite our imaginations on what this could be. And what I'm trying to define is some kind of a lifting, or I don't know what the right term is, but I'm trying to drag the shadows of the circle operation into this square operation. So I think what they call it is a linearization of the circle operation being reflected in the square operation. The point is that the square operation takes two things in k to the x and returns something in k to the x. But I don't want to define a completely arbitrary binary operation. I want to define one that is sufficiently related to my base operation, my base binary operation on x, so that when I manipulate things in this vector space, I can meaningfully reason about the base circle operations. I want some connection. And the question I was trying to ask is what would be a natural connection? And I think Jayati also has a suggestion in the chat: get the index from the table and then do multiplication. So let me just say what I have in mind, and maybe you can check if that tallies with what you were thinking. And maybe Jagdish, you can also let me know if this makes sense. But I'm going to simply define this as, well, when you're trying to define, the box product between E of something and E of something else, that something and something else is sitting in X, right? So I will multiply them in X using my familiar circle product, and the circle product gives me an element in X, and I will use E as the vehicle for traveling back from X to K to the X. Okay, so I multiply heart and spade to get a heart again. I cannot report heart as the product of these two vectors, because like when I was just saying, I want a vector, I don't want a scalar. So heart it's not even perhaps, it's an element of X right now, and I want to go back from this element of X to some element in K of X, K to the X, and I'm going to use the mapping E to do that for me. So I'm going to map this to E of heart, and I don't know why I'm doing these completely absurd doodles when I have it in the next slide. So let me try to see if I can advance the slide. So this is going to be my outcome, and in general, this is going to be my definition. My definition is going to be that whenever I see EX box product EY, I'm going to replace that, or I'm going to define that as E acting on the circle product of X and Y. So let me know if this makes sense. So this is defined as this. And now you can plug this in to define the box product for any pair of vectors, because yeah, I mean, that's basically how we are defining the box product of any pair of vectors as well. So for two basis vectors, we define the box product as E acting on the circle product of the natural ingredients that represent the basis vectors. And now if I have to define the box product for any two vectors, I do it in terms of the basis vectors. So let me know if this definition makes sense. And then I will do some blah blah about the text below the definition. Basically, the idea is that this construction is designed to amplify the violations of non-associativity. What we are really hoping to achieve here is that if there were teeny tiny violations of non-associativity in the base table, if you lift it to this big vector space, then those non-associative triplets basically manifest in a much larger number, so that our random pinging idea will basically work if we were to apply it in this bigger space. So that's just a lot of words. We are going to try and make this formal. We're going to try and quantify these ideas in just a bit. But let me know if the definition of the box product makes sense. So we could have just defined this. In fact, this is what Mathujek also says. We could have just directly presented this definition and said, we're done with it. But I think we just build it up in a couple of steps, just so that hopefully it feels natural. I think that's the reason why we belabored this a little bit. But yeah. So Jagdish, is this adding up, or is it kind of still unclear?
I'm still wondering how you combine two vectors in this vector space. Like, what is U1 plus V2? What is that operation in your vector space?
Oh, U1 plus V1 would just be like apply the entries of the ith entry of U1 and the ith entry of, let's say we are trying to combine U and V, the natural with the basic vector space operation. You take the ith entry in U and the ith entry in V, and you add them up as you would add them up in F7.
Okay, if that is the case, then why don't you just refer to this as F7?
Refer to what as F7?
K as F7.
Oh, I should have probably done that. Yeah, K is, so I have K on the top right as an annotation, just to remind us it's F7. But yeah, think of K as F7, that's fine. I think Mathujek says that it could also be potentially a different field and the calculations still go through. And K could potentially even be R. I haven't actually double checked how the probability calculation goes through if we work with a larger field. But yeah, for now, I think just for ease of operations, we are going to fix K to be F7. So yeah, if that feels easier, then sorry, did I say K to be F7? Yeah, K to be F7 indeed. So this is I don't know if I have K to the X written out on these slides, but yeah, this K here. Yeah, n tuples of numbers from K. Think of K as F7 throughout. That's fine. Yeah, so with that, if that helps, then yeah, let's just do that. Yeah.
Yeah, so, I mean, then it's just a normal vector space.
Yeah,
I thought there was some catch with the that's why you're using K or something.
Yeah, no, there's no funny business going on with the vector space at all. And like, we've had some weirder ones in the past, but this one is just your friendly neighborhood vector space. This is fairly routine. In fact, the indexing can also be thought of as just 1 to n, except that in our minds, just so that we can be transparent about how the box product is being defined, instead of thinking of the index as 1 to n, you think of it as the elements of X. But yeah, that's also really not a big deal. So you could just think of it as F7 to the n. That's fine. And that's the vector space we are working with. But yeah, we are trying to define, I think the key thing is we are lifting the circle product from X to this box product on this vector space. And we are hoping to amplify violations of non-associativity in K to the X. That's kind of the goal. Yeah. So if the definition, are we happy with the definition of the box product? I think we got a couple of plus ones when I asked that earlier. So hopefully a sign for me to move on. And let me know if anything is still weird. But yeah. Okay, so here's our randomized algorithm. It goes more or less as you would expect. The idea is to the idea is to basically test for non-associativity across random triplets. Let's just make this explicit. So we're fixing 6 elements from F7. Okay, that this can be anything. Again, I don't know if, so like I said, you could do a mental exercise of, just using R instead of K and checking that everything goes through. I don't know if it'll go through as is or with minor tweaks, but for now, let's say we've fixed 6 of our favorite elements from this field, okay? And 6 will actually play a role in just a bit. So it's important that we fixed 6 elements. And now for every element in your base set X, pick 3 elements from S uniformly at random. We're picking 3 elements just so that we can plug these into the 3 vectors for which we will be checking, on which we will be checking for non-associativity. So anyway, let's just imagine that. So for instance, we had our hearts, diamonds, spades, and clubs. So for each of those guys, we have 3 elements from S picked uniformly and independently at random. And now we are going to, these are the vectors that we are going to ping, okay, for our non-associativity check. So U is basically, so remember that we have 4 of these basis vectors in our example, right? So we are going to weight those basis vectors with the alphas, right? For V, we are going to weight the basis vectors by betas, and for W, we are going to weight the basis vectors by the gammas, okay? So we are going to, basically, this is why we said we are picking 3 for each element of X, because those naturally give us 3 vectors. So it's this construction of which are the 3 random things that we are going to ping for our non-associativity test. Is that clear? We're going to, these are the 3 vectors for which we're going to ask them, are you folks in violation of non-associativity? I mean, are you folks in violation of associativity, meaning are you non-associative? So this is what we are going to do. So is the mechanics of the algorithm clear? We have basically constructed 3 random vectors in K to the X. That's all that we have done. We have picked, I think maybe I could have simplified this notation in retrospect. We basically picked, so 3 vectors in K to the X is 3n things, right? It's each of these is n coordinates, and each of those are entries from F7. So we have basically rolled a 6-sided die for populating each of those entries. So we have 3 random vectors, and now these 3 random vectors we are going to check if they are associative or not. Okay, and you can think a little bit about the time this takes to do. So U and V are, so you'd have to basically compute this box product, right? So this is going to be, this is a sum which has n squared terms. So each of those box product computations takes n squared time. And so that's 4n squared, and then checking if they're equal, that's n equality checks. So that's ordered n squared overall. So let me know if you're convinced about the mechanics of this algorithm being just an n squared algorithm. And hopefully it's clear what the algorithm is doing. Okay, so thanks. I think I have a go ahead from the chat. So thank you. The output of the algorithm is exactly as you would expect. If these guys turn out to be associative, we actually declare our base binary operation to be associative. Otherwise, if we have a violation here, we say no. So if we can, so again, one question is, when can we be sure that we are doing okay, and when are we uncertain? So so if we say no, clearly it means that okay, it requires some working out, which I did only on pen and paper, I'm afraid. But anyway, it's not terribly hard to check that when you're saying no, it's because So we have a visible violation of associativity in this big box operation, but you can trace that back to a violation of non-associativity back in the circle operation. And that you can do just by symbol pushing. You write out the box product and you say, okay, if these vectors are not equal, they're not equal at some coordinate, right? And when they're not equal at some coordinate, you can trace it back to 2 elements back in X, in fact, 3 elements back in X, which are not associated. So whenever the algorithm says no, you can be super sure that you're doing fine, because there's a visible violation of non-associativity that was witnessing the no answer. But if you say yes, it could be because the operation is genuinely associative, or it could be because this choice of U, V, and W was simply misleading, right? This choice of U, V, and W somehow lulled you into thinking, yeah, okay, we don't see a violation here, and we have concluded that our whole operation is associative. It's possible that you just missed a violation, right? So is this clear that the no answers are always fine? They're solid. You can trust them. The yes answer may be like, meh, you're not sure about this. So, and you're going to argue that you miss violations with probability at most 1/2. That's the last part of this argument. So give me a +1 if you're good so far. And then we'll try to relate this to the zeros of non-zero polynomials in some way. Okay, all right, thank you. So, this is now our final claim. If the base operation is not associative and we make these random choices, then we will detect this non-associativity with probability at least 1/2. Okay? And I think our starting point is kind of similar to, I think, the kind of alternate argument that Vinay was making at the end of yesterday's discussion. So let's fix a violation of non-associativity in X. So let's say ABC is the non-associated triplet with respect to the base operation. And now imagine that we've made all our random choices. So remember that for every element in X, we picked 3 things at random from S, from our 6 elements of the field. So we pick 3 things at random. So assume, in fact, that we have made all of these choices and fix them to being arbitrary choices. Don't really care. And for ABC, we are going to now think of, for these specific elements, which are the elements that are giving us trouble. These elements are not associative. We're going to think of the choices that we made for them as random variables, and we are going to sort of work with those. So we're going to pick from A, we are going to pick alpha A, from B, we are going to pick beta B, and from C, we are going to pick gamma C. So again, let me just maybe go back to this notation here. So remember that for every X, we picked alpha, beta, gamma. So for A, we would have picked alpha A, beta A, gamma A. For B, we would have picked alpha B, beta B, gamma B. And for C, we would have picked alpha C, beta C, gamma C. So there are these 9 elements, 9 random choices associated with the 3 things that are in violation of associativity. We would have made 9 random choices. From those, I want to fix, I want to focus on 3 random choices. In particular, I want to focus on alpha A, beta B, and gamma C. Okay. And we're going to say that, okay, if, fix all of the other choices and treat these as like, these are the final random rolls of dice that we make. And even with respect to, so for any choice of the other, for basically, any or every choice of the other elements of the other numbers. So remember, we said that we have these 3n slots, which we are trying to fit with numbers, right? So instead of thinking of them as random events, fix any set of numbers that you want, except for keep these 3 slots reserved as really random choices. And we will show that under the simplified experiment also, the probability that this non-associativity will actually come out is at least 1/2, which is what we want. It's a valid lower bound. You could have more violations of non-associativity in the base operation. That'll only improve your probability claims. So this is fine. And in fact, we've seen that in the worst case, we might we might be working with operations that have exactly one violation even. So this is fine. I think this is a good place to be. Let's say that we've fixed everything. We're just working with these 3 random choices. And now the question is trying to understand what this box product looks like. We're going to, in particular, show that, well, if these things are not equal, that also means, so remember that this box product is an element of k to the x. It has n coordinates indexed by x, elements of x. So we are going to focus on this element here, which is given by the product of A, B, and C, or the circle product of A, B, and C, with the bracketing being A, B first and then C. So on this index, we are going to say that these entries are not going to be equal with probability at least half, which basically means that we have to understand what this looks like. And if we had a little more time, I think I would have actually paused here to try and see if we can maybe work through this pen and paper. So here, maybe what I should have done is also expanded this definition to the 3-way thing. But yeah, maybe let's think about this, right? So U box V at R, what is that? What is that going to be? Do we have? I think it's kind of useful to do a quick pen and paper calculation here, right?
What does the subscript mean?
Oh, I'm looking at, so this is a vector. This thing here is a vector in k to the x, right? And we said, or if you like, sorry, k to the x, which if you like, you can think of as f7 to the n. So this subscript here, r, is an element of x, right? So I'm looking at the entry of this vector corresponding to which is indexed by r, and r is an element of x. It's this product here. Does that make sense?
It makes sense for the LHS, but for RHS, why is, because that may not be R, right?
Well, the thing is, these are both vectors, and both the LHS and RHS are vectors in k to the x, right? If you drop the r, these are both. So with our kind of example, maybe on the left-hand side, you have something like 3, 2, 0, 1. This could be the vector that we get by executing this product. And maybe on the right-hand side, we get something like this. So these are both vectors in, so they're both vectors being indexed by, so what is my index? Yeah, I don't know if I can get this to align, but my index is heart, diamond, spade, clubs, something like this. And here also it's heart, diamond, spade, clubs. My index is elements of X, right? And in my running example, X was the 4 suits, right? So the first index is for the heart, the second one is the diamond, and so on. So what we are saying is, well, suppose we are looking at A times B times C, let's say heart times diamond times spade, and let's say that turns out to be clubs. So we are saying on both sides, look at the element that's indexed by clubs. That's going to be different with a decent probability. That's what I want to say. Yes, I don't know if the notation is sensible or not, but both of these things here, unless I've terribly misunderstood something, both of these things here are vectors of k to the x, right? So they all have elements indexed by x. They have n coordinates. Each of those coordinates is in 1-to-1 correspondence with some element of x. So it makes sense for me to look at the rth coordinate, which is the coordinate corresponding to this element of x. Is that okay?
Yeah.
Okay, good. Okay, so we want to say that these things are different. All this amounts to is kind of unboxing this box product and trying to figure out sort of what's going on. And you could think of it as, well, okay, let's see if Yeah, so really, I think, you can look at the definition of the box product on the top and really just try to focus on your favorite index. In this case, R is the index that we want to focus on. So this is a sum of things. Each of these things is a vector in k to the x. So these are also these vectors are also indexed by elements of x. So just try and shine a spotlight on the entry corresponding to, the entry that is indexed by R, and that's all that we want to focus on. But remember that most of these XY pairs here are really fixed for us because we have kind of, we're playing around here with entries. So U and V both have, if you put together the entries of U and V, we are staring at 2n things, of which 2n minus 2 things are fixed constants for us right now. There are only 2 things here that are random. The first thing is alpha A, which is something that shows up in U, because remember, U was chosen to be all the basis vectors indexed by the alphas, V was things indexed by betas, and W was things indexed by gammas. So if you now look at U, V, and W, basically pretty much everything is fixed except for what? Except for when I look at alpha A here, this for me is a random variable. If I look at beta B here, this is a random variable. And here, if I look at gamma C, that is a random variable. So really think of these as vectors with 4 entries or n entries, where everything is now fixed constants, except there's 1 entry in each of these guys, which I'm thinking of as a random variable. Okay, so those are the 3 vectors that I'm dealing with. So when I look at this product, the purple expression on the top, most of these things are just going to, they're just going to collapse as constants. And let me just make a claim about what survives as a variable expression. So okay, so in fact, conveniently, I think the notation here is basically saying, okay, let's look at remember we talked about the rth index, right? And so we are saying, well, look at this product vector, look at the rth index, and let's denote that rth index as being the function of alpha A, beta B, gamma C. That we can do because of what we just discussed. What we just discussed is, in these 3 vectors, everything is fixed except for these 3 locations. These 3 locations being these 3 random variables, right? So we can really think of this rth index as being some function of these 3 random variables. And in particular, those functions basically look like this. This, I think, there's like a couple of steps of computation that have been gobbled up here, but it's something that I felt that I did manage to verify. I mean, it's like I said, it's a lot of symbol pushing, expanding out the sums, and collecting terms that involve that involve the index of interest. So these are basically this would be the thing that survives to give you what's going on the coordinate. For now, again, mostly in the interest of time, and also because this is really just computation, and I don't think there's I mean, I really feel now that maybe a worked out example here would have been nice. I should have worked through one of these, actually taking an instantiation of what the algorithm might be doing so that this was more visible. But anyway, the point is that if you believe this expression to reflect the rth entry in these two vectors, in these 2 output vectors, the bad event for us, the thing that we would worry about, is these guys collapsing to being the same, because we want to claim that this rth index was different for these guys with a decent probability. So what can we say about that not being the case? That not being the case would be that these guys are equal. Now, if these guys are equal, that again means that the difference, so think of this as sort of a polynomial expression. Again, it's a multilinear polynomial, basically, in these, so it's, it's a multilinear polynomial, which now, what we are saying is because our base operation is non-associative, this difference polynomial is actually a non-zero polynomial. But the fact that we see same entries at the rth index, that means that we have chosen to pick random values for these fellows in such a way that we have actually ended up with a zero of this polynomial. Okay, so this is a degree 3 polynomial. It's a non-zero polynomial of degree 3. We have picked random entries from a set which has 6 elements. So the chances that we have hit a zero of this polynomial, knowing that it's not, so we know that it's non-zero because XYZ was a violation of non-associativity in the circle operation. So we know that this polynomial does not collapse. Okay, so we know that this is a non-zero polynomial, but somehow the bad event is that we have picked values for these 3 random variables in such a way that we have hit a zero of this polynomial. But degree 3 polynomial, we have picked values from a choice of 6 values, right? So the d over s, d is 3 and size of s is 6, so 3 over s is 1 by 2. So that's where you get your success probability being at least half from. My personal feeling is that one thing that may not have come through is the claim about this expression for the rth index of the box product of these 3 vectors taken together. I think I should have either written out that calculation or maybe shown it through an example for it to be more convincing. I'm kind of okay with this because I scribbled something, quickly just before putting it on the slides, and I was like, this seems to check out. And if you find it fishy, I would invite you to do the same and let me know if it's kind of not clear, and I'll see if I can expand on these slides to include a worked out example. Maybe that makes it nicer to see. But hopefully, philosophically, what's going on is, okay, 2 main ideas. One is that, well, non-associativity can be a very small needle in a very large haystack with a base operation, the circle operation. So you try to amplify the needle relative to the haystack by moving to this k to the x space, where non-associativity manifests in larger amounts. And that is all that we are trying to prove here, that actually works as advertised. And the way to do that is to, instantiate at an random place and say that, well, you wouldn't have, if there was a violation of non-associativity, then that would have manifested as a non-zero polynomial here. And if you failed to catch it, that would have amounted to hitting a zero of a non-zero polynomial. So that would have happened with low probability, which is the quantification for this idea that examples of non-associativity have magnified in this space. So yeah, that's kind of a high-level summary of what's happening. Sorry if the notation was a bit messy on this one, but let me know if you have questions or comments. I will stop talking at this point.
Since you don't know R, you have to check this for each coordinate, right?
Okay, so I think this is an in-principle argument that if there was, so this is only in the analysis of the algorithm, we are saying that, so something would have manifested, right? If your base operation was
you have to check for each of the
the algorithm.
You just keep checking. You first pick your random points, and then for each coordinate of this, you check whether you got a non-zero. Right?
Yeah, absolutely. So I think the algorithm will definitely check the entire vector. So it'll check all the coordinates. So that's n squared operations to compute these 2 vectors, and an additional n equality checks because you're going over all the coordinates. That's absolutely correct. Yeah.
Yeah.
Okay, so yeah, I mean, hopefully at least the mechanics of the algorithm came through, and this very high level idea of, trying to magnify the event that we are trying to catch by doing this, whatever lifting construction. At least that's in a fuzzy sort of way. It's the approach comes through. The details, I think some of it, there is some stuff that I probably should have put in more explicitly, and that's something that I hope to fix in due course. But yeah. Vinay, did you have any closing thoughts? This whole setup?
Yeah, I think too many subscripts, I think.
I know, I think,
So
yeah,
I think it's
it's a bit overwhelming. Yeah. No, I think, yeah, it's a bit lazy about just, think following, just sticking to the notation in the miniature. I think that an example, even an abstract one, maybe a running example would have made this, clearer. Actually, I think it is a nice set of ideas. It's not, yeah, I mean, I don't think it's awfully, it's probably clever for sure, but it's not, I don't think it's as incomprehensible as I've made it out to be. I think it's actually, yeah, it actually feels like it goes through once you
yeah,
work.
I think some pictures maybe would have helped. I think
Yeah, I agree.
maybe. I think instead of too many subscripts, too many symbols floating
Sure.
around, it's unclear. Yeah.
Okay. Yeah.
I mean, I got the argument, but I probably wouldn't have written this f of alpha a or whatever you had in the next slide, right? Yeah, that seemed to.
Yeah. No, I think the idea with that was to compactify the notation involved in, reasoning using short people. I think
There's a question, I think, what might be an obvious application of such an algorithm? What's a possible application? I don't know. So, yeah, may not be compile optimization. I don't think. I think compile optimization, I don't think will usually hit this sort of problem there. So.
Maybe, yeah, I don't know. I think in the miniature, they're very hand-wavy about this, saying that a group, an algebraist might be interested in this. I don't know, like maybe people who work in computational aspects of, I don't know, algebra, computational.
Yeah, I mean, if you look at any finite algebra, you probably want to know if you invented something. Yeah, so there are probably places, but.
Yeah, but maybe a bit, I mean, yeah, I can think of like a...
Yeah, okay. So I think closing comment. So you mentioned something at the beginning, you said something about octanion or something, right? Did you?
Yes, I did. Cayley's octanions is what is given as the nice example of violation.
Yeah, so there is something nice there. It turns out that powers of 2 have something interesting. So the only way to take R2 and convert that into a field is to make it into a complex plane. And then you can ask, can I do it for higher values? And people spent a lot of time trying to do it for R3 and they couldn't. And then Hamilton figured out that Hamiltonian, so William Hamilton, the person who did the Hamiltonian cycles and so on, he figured out that, and Hamiltonian in physics as well, that you can't do it in R3, but in R4 you can do it. But you have to give up commutativity, and that is the quaternion. And then it turned out that R5, R6, R7, you cannot get a field structure or any structure similar to a field. R8, you can do that. And you can get some structure. And that structure happens to be an octanion. But you have to give up associativity there. So it's really not a field.
Wow.
Okay, so you have to give up one, an arm at each level. And octanion is as far as you can go. You can go to R16 and there are some very weird structures out there which you can, which exist. But R8 is as far as what people go in this series. Yeah, so octanions are nice. Nice in a sense, they are probably the last of the nicest things you'll find.
I see. Okay, that's fascinating. It does merit yeah, I mean that's a great advertisement for looking it up further. So okay, all right. So thanks. That was great trivia as always. And yeah, so I think yeah, just while folks are still around, maybe I'll just make a housekeeping announcement about the fact that we're now in December, and I think we had a good run, hopefully, by and large. And because of constraints related to travel and other logistics, we might just have to call it a day on this one without being able to go all the way till the end. But so tomorrow, I think is when we call it a day. So tomorrow, I will probably skip ahead to miniature number 30, simply because it circles back to something we've already seen before. So when we did only 2 distances, we talked about what about 1 distance, and miniature 30 is somehow about that. And also the next 2 miniatures are kind of related to each other. So I didn't want to pick up one of them and not finish the story. So that would leave us with, I think, 5 miniatures that we wouldn't have gone over. And if you folks don't mind, maybe we can do like a quick reunion week sometime in January, post-holiday season. And I think that would be just as well, because these 5 are kind of a little more non-trivial than the average miniature, and I think I also will probably not do justice to them if I kind of rushed them through over the next few days in December. So that's the plan. We are going to meet once more tomorrow to do number 30. And if everyone's still up for it, then we can meet for a week sometime in January on the other side, and knock out the other 5. So that would be nice to do. So once again, yeah, I'll do a more elaborate thank you tomorrow, but this is just a heads up to say that tomorrow will be like a bit of a mini closure on at least the current run. So so maybe see you then, and we'll talk about equilateral sets. That's what's coming up. Yeah. Okay, so on that note, we'll stop here and see you once more tomorrow.